In this exercise, we have a question about the volume of a region in n-dimensional Euclidean space. And so basically what we have here is that the volume of this unit ball for in Rn is given by this region here, which is a ball of radius 1. It's centered at 0, and the volume of this ball is given by this equation here, where this is the gamma function defined as this integral here. And we're given a set of information about the behavior of this function, which hints and gives information about how to sort of solve A, B, C, and D here. And the real question that we have, I mean, the critical question here is that we are asked to find the probability that u1, u2, un, and they're defined as these random variables, uniform from -1 to 1, is in this unit ball, Rn. And then there is a question about evaluating this numerically, and then squeezing this region a bit, and then asking what happens when we increase the number of random variables to infinity. Okay, this sounds like a lot of things going on in this question. Let's break it down into its critical components. So starting with A, and what we have here is, I think it's easier to start with 2 random variables. I mean, we have n of them. Well, let's figure out what happens if we want to calculate the probability of u1, u2 are in the unit ball. I'm just going to call this ball like so. It's big O or big 0, depending on how you see this. And how do we think about this question? One way to do this is that let's draw the support and see if we can simplify it a little bit, or at least get some insight about what is going on here. So we have the support of u, this is u2, u1, and then the support of u1, u2, we know that it goes from 1 to -1, and same here, 1 to -1, and this is given by the distribution of all these random variables. So drawing a square here, like that. Oh, it was a little uneven, like so, like that. Okay, it's almost a square, but you see what I mean. And this is the full region, the full support of u1, u2, and then we're asked, or we're going to check what's the probability that these two fall into a circle in this support. So let's draw a circle inside here, like that. Let's see if it gives us a circle. Yeah, okay, pretty much a circle, but let me just, okay, so it's not an even square here. Let me tidy this up a little bit. This looks a little ugly. Redraw this part of the okay, all right, it's not very aesthetically pleasing, but let me see if I can do it again. Okay, so let me just, you see what I mean, and this should the circle should be in the middle like so. So this circle should hit or touch the end of the support on this side, that side, and this side. Okay, so we want the event is valid if it falls into this green region, the circle, and it's invalid if it falls outside this region. There. And luckily, we're dealing with a uniform, so uniforms, so we can divide the density of the circle, the square, with the density of the circle, and that should give us the probability that this event is true. And the probability of the circle in this two-dimensional case, it's the area of the circle, A, let's call it A, divided by the joint density of U1, U2. And the circle in this two-dimensional case is pi r square. R square is the is this span here, and that is 1 by the information given in the in how this unit ball functions, right? It's up to 1, so it goes in that direction, and f of u1, u2, so the joint, they are independent. That's given by this statement here. So we can multiply now the joints of, so the marginals of f. So basically that's half, and then we said this is 1. So the whole thing here is pi, this probability is pi divided by 4. All right, so that gives us pretty nice information about what happens in the n-dimensional case. In the n-dimensional case, I mean, we're still dealing with the same principles, but obviously it'll get super difficult to draw this, but the principle is the same. And now the unit ball, the volume of it is given by this Vn and the whole gamma function business here. So the general case is so the probability that u1 up to un is in the circle, the same thing as Vn, so that's the volume, divided by the square. And the square, I mean, you know, if we look at the joint here, it doesn't matter how many ends we have. We can have n of them. And so we can now multiply their the number of times they appear. So that's that is basically the square in n dimensions, and this is the volume in dimensions. And that is indeed the answer. I mean, we could write out the Vn thing, but I guess you see what I'm trying to hint at here. Okay, so let's move on to the next question here, and that is about computing. Well, let's see, where is it? It's about computing. You're going to evaluate this, asked to evaluate this numerically using R, and I'm going to leave it up to you here, because I'm more focused on doing the mathematical part of these questions. But basically, there's a gamma function, and then you have a vector, call it 1 to 10. You write a function that takes this whole thing, write it up like so, and then plot for all those 1 to 10 n values. Okay, so A, B, and so C here. Now we are letting a constant C be within 0 to 1. We're going to let xn count how many of these ui's satisfy the condition that they are larger than the c. And then we're asked what the distribution of this xn value is. So what does it mean here? I mean, let's first figure out what the probability of any one y falls into outside this region of interest. And basically the way to figure out where, I mean, c here is basically a, let's take red, c is basically a value here somewhere. We're asked to evaluate where, you know, if it falls outside this region, like that. Okay. So the probability of the absolute value of uy is larger than c. That's the question. That's the probability that we want to evaluate. Sorry, we're going to evaluate the xn case, but we start with figuring out what that value means. And that value means essentially here that we have a region which is of a specific length, and its length is 2. So in the one-dimensional case, this is just 2, and we're looking at where c is laying, and this can be viewed as 1 minus c 2 times. So we have 1 minus c 2 times, and this probability for any one u is 1 minus c. Now, because we're looking at the number of u's falling falling into that region, but we're looking at them independently, so we're counting the number of ways this can happen, we're really looking at a binomial distribution here. So this follows clearly the story of the binomial, let's say. So the probability, or xn basically, xn is distributed as binomial with n random variables and trials 1 minus c. Okay. Now, heading for the last question here in D, we're now setting c to 1 divided by square the root of 2, and then we asked to figure out what will happen as n goes to infinity. Okay, so let's figure out how to think about that. So what we have is we know that the probability of anything has to be larger than 0. Okay, and we also know what the volume, the probability that let's see, where is the, yeah, where this probability here, let's copy this, duplicate it, that unpacking this a little bit, we see that we get, let's write down the whole expression from here. So where is it? Okay, so here, and right, just checking certain values. Okay, so we will figure that we have root, oops, we have gamma n divided by 2 plus 1. That's what v is, and then we have pi n squared, and then we have that multiplied by 2n. Okay, and that is if we only focus on, because we know that this is, we only focus on this part because this is always positive and we're dividing by it. If we only focus on pi n, let's do the following. This is the same thing, n 2n. We'll see that this function will grow faster as n goes to infinity than this part here. So this goes to 0. And we can see this by, I mean, already if you look at pi here is 3.14, and as we go even for n equal 2, this starts to outpace it. Imagine this going to 10. We have a value that the denominator growing much faster in the end. So this shows us that by squeezing in this whole expression here, that this will go to 0 as n grows to infinity.